All right, are we ready to do rock and roll here? Okay, so let's do the problems. The first one, I have 50 meters, 500 meters tall, yes? And I have the velocity of 200 meters per second, right? And I want to know the dx. What do I have to do? In order to find dx, what obvious equation are you going to use? You're going to use this one, right?
Yeah.
So I need tx, right? Isn't tx and ty the same? Okay, so let's use this equation here to find ty, which is the same as tx, correct?
Yes.
All right, so plug it in. What do I get? I get ty equals tx equals what? 500 divided by 5. So tx is going to equal 10 seconds, correct? So what is 10? 10 times 200 is 2,000 meters. How many meters in a mile for
1,000 meters. Around 2,000 meters.
1,600?
Yeah.
Significantly different than that, yeah. 1,600 meters in a mile. Okay, so it's substantially more than a mile, right? Okay, next, I want to find dy. I want to find dy. I have dx and vx. Remember, v naught and vx are the same. Therefore, what can I find?
Dx.
Tx. So dx over vx. So 10,000 meters over 1,200 meters. T is going to equal what?
25 over 3.
What is it?
25 over 3.
Okay, but can you give me a decimal equivalent?
8.33.
What is it?
8.33.
8.33. We'll just say 8.3 is fine. Right? Correct? So now what? 8.3 is the time. Now what?
8.3 squared times 5.
Okay, so dy, that's what I'm looking for, is going to be 5ty squared, right?
Yes.
So that's going to be dy equals 5 times 8.3 squared.
347.2.
What is it going to be?
347.2.
Close enough. Yes? 347. Yes? Is everybody okay with this? Melissa, how you doing over there, all right? You doing all right? Good. Excellent. All right, now, I have to find V naught. So what two things do I need to find V naught, which is really Vx? What two things? What is it? What? Dx. So I want to say Vx equals dx over tx. So, right? All right, now, I know what dx is. 16,000 meters over tx. So I've got to solve for tx, right?
Yes.
Well, I know this is 1,000. Right away, I know it's going to be what?
You're gonna do 200.
10 root 2.
Yeah. What is it?
No, start with.
No. What is for 1? What is it? What's it for 1? What is it for 1? If something's going to fall 1 meter, how long does it take?
5 seconds. Wait, no.
1 second.
No.
1,000 divided by 5.
Yeah. I'm just asking you to go with this. Do it in your calculator. 1 meter. 1 divided by 5 is square root of 1 divided by 5. Dan.
There's like 20 people doing it, so like I know I'm not gonna get it first.
Well, but, oh, I thought you did it. I'm sorry. I thought you did it and just like holding back. It's okay if you don't get it first. Okay, we're not playing Jeopardy. Okay, we're not ringing in. Okay.
Yeah, 0.45. 0.45.
Okay, 0.45.
Yeah, that seems about right. For a second. It's less than half a second.
Okay. What about 100 divided by 5? Square root of 100 divided by 5.
2 root 5. Which is 4.47, which is, yeah.
That's 20, square root 20. 2 root 5.
So that would complicate things.
Because I'm trying to, okay. What is the square root of 2?
1.4.
Square root of 2 is 1.4, right?
Yeah.
Okay. What's the square root of 0.2?
0.447.
Okay. What's the square root of 20?
4.47. Yeah.
Okay. So if I have 1,000, so you're going to plug 1,000 in, right?
Yes.
Right? So 1,000 divided by 5, what's the square root?
14.14.
14.14, right? See the connection or no? Okay. All right. So I'm going to put in here 14.1 seconds, and that's going to be what?
1,131.
1,000.
131.4.
1,100.
Yeah.
I'm running out of trying to squeeze things in here. So it's going to be
1,000.
1,000.
131.37 or
That's fine.
0.4.
No, no.
Okay, 1,000.
You're going to be taken away at night by the significant figure police. 4 is more than enough. I actually would say 1,130 would be better. You know, 4 significant figures is really an absurdity. It's a little weird. Okay.
Well, it depends on how many significant figures you start with, and then you're supposed to.
No. You're absolutely correct. If it were a conversion, you're absolutely correct, Brianda. Absolutely. My point is 2 things. One, if you have a lot of significant figures, that means your instrumentation is pretty good, and we're just trying to get the point, really. You know what I'm saying? I mean, if you're talking about bombs, first of all, do you need a lot of significant figures? No, because it doesn't have to hit the spot, does it? You know, it's going to get you. Yeah, it's kind of sad, isn't it? A little weird, but the rule that I use is always no less than 2, no more than 3. It's fine. Okay? Yeah. The problems will be certainly different enough where, you know. Yes, Daniel?
A lot of physicists working on nuclear bombs and stuff like that.
Well, first of all, I'm not talking about nuclear bombs. You really don't have to be anywhere near where it's actually going to hit. First of all, nuclear bombs don't hit the ground when they explode.
They go before they hit it.
Oh, yeah. The one, I think, if I recall correctly, my math, I think the one that blew up over Hiroshima was, I think that exploded 500 meters above the ground to get the full, oh yeah. They're called, I mean, I'm not sure that, you want to know a little bit about bombs, even though it's a little depressing, but it's called proximity fuses. That was something that the Allies invented towards the end of World War I. They were employed in like the Battle of the Bulge. They were very, very good in terms of the soldiers in Bastogne were outnumbered, you know, by a lot, and the Allies employed something called proximity fuses, where when a bomb hits the ground and digs in, it just hurts people that are near them, that are near the explosion. Whereas if it's going to hit like 6 feet high, then it's going to be able to, well, send a shockwave, yes, excellent. But the shrapnel will be able to go farther in various directions. Yeah. It's kind of nasty if you think about it. So when you're talking about significant figures, 3's fine. Trust me. Okay? 3's fine. Especially when you're talking about, difficult to talk about projectile motion when you're, why did they come up, what precipitated, what compelled scientists, who supplied the money? No, when they first experimented with projectile motion. A scientist needs money, right? You know, a scientist doesn't make money necessarily. They're usually funded by somebody, okay? You always follow the money, okay? If you're looking at research that says a widget is bad for you, okay? A widget is bad. Bad, bad, bad. And the widget company is probably not funding that research. That's probably funded by the anti-widget society. If you get this research that says widgets are excellent for you, the money is probably coming from the widget company. So when you're talking about projectile motion, you're probably going to find the money's coming from a government who wants to invade another country so that they can take their natural resources. Because isn't that really what warfare is all about? It's either driven by religion, the need for land, or the need for natural resources, right? Yes? Yeah, it's kind of sad, isn't it? So, all of this, you can go back to Tartaglia, remember the scientist Tartaglia? Well, he was funded by, Renaissance and early Renaissance governments when he came up with cannons and how to hit the broadside of a castle with a cannon, and predicting and things of that nature, and understanding trajectory and projectile motion. Yes, Alan? A widget is just a fictional item that can be used as an example to get a point across that has nothing to do with necessarily the design of the individual component you're speaking of, such as a widget. A widget is just a fictional thing, a widget. There was a movie play, How to Succeed in Business Without Really Trying, or something like that, and they made widgets. It's just a kind of a comical thing. All right, hey, Wednesday, be here. See you later.